Hi everyone. We are continuing our discussion of trig functions and their values for special angles. Before, we discussed the special angles from 0 degrees to 90 degrees, or from 0 to pi/2 radians. So for example, let's take a look at 30 degrees here. This 30-degree angle. The terminal side of the standard 30-degree angle intersects the unit circle at this green point. The x-coordinate is the cosine of 30 degrees, √3/2. The sine is the y-coordinate. The sine of 30 degrees is 1/2, the y-coordinate. Remember, sine of 30 degrees is 1/2. That's a basic fact you should remember. So this piece of the unit circle gives you the cosine values and the sine values for these special angles from 0 degrees to 90 degrees. And it turns out that these principles extend to the other quadrants and to the other quadrantal angles. Here, we're looking at the special angles in quadrant 1 and the nearby quadrantal angles. But we're eventually going to be able to look at all special angles with nice reference angles, the brothers, for all these. Okay, now these cosine and sine values can be encoded in the table, which you should be able to write pretty quickly. And there are patterns that we discussed last time. Now, we're going to extend our knowledge to the other quadrants. And again, we're going to organize the non-quadrantal angles in terms of families, basically families of brothers. Brothers, or we could refer to them as co-reference angles. That's not quite standard, but it sounds more professional. Co-reference angles. I like to call them brothers. You can call them sisters or siblings. These are angles that have the same reference angle. So for example, these four angles here. And I'm going to talk more about radian measure because it turns out that radian measure is actually more convenient if you want to hop from quadrant to quadrant. We have here an acute angle, 30 degrees or pi/6 radians. This is an acute angle, and the reference angle for any acute angle is itself. The reference angle of 30 degrees or pi/6 is itself, 30 degrees or pi/6. And we know the cosine and sine for this special angle from the table or the unit circle. Now we can use that information to tell us about what's going on with its brothers. There are 3 other brothers for pi/6 between 0 and 2 pi. These are the most famous 4 brothers that have pi/6 as the reference angle. The ones between 0 and 2 pi. Actually, negative pi/6 is also pretty famous. That's also in quadrant 4. It's coterminal to 11 pi/6 over here. But we're going to start with the special angles from 0 to 2 pi radians. And why are these brothers? Why are these co-reference angles? Because they share the same reference angle. A reference angle is an angle that a non-quadrantal angle, so we don't want like 90 degrees, it's the angle that a non-quadrantal angle, if you look at the terminal side, the angle that the terminal side makes with the x-axis. And it's always going to be acute. By definition, reference angles are always acute, like 30 degrees. So here, the 150-degree angle, or 5 pi/6 radians, that has the same reference angle, 30 degrees, or pi/6 radians. This acute angle is the common reference angle for all 4 of these angles, 5 angles if you include this over here. Again, over here, for 210 degrees, or 7 pi/6 radians, we have the same reference angle, the angle that the terminal side makes with the x-axis. Over here, for both 11 pi/6 and negative pi/6, we have the same reference angle, 30 degrees, or pi/6 radians, between the terminal side and the x-axis. Again, I refer to these angles, all 5 of these, as brothers or co-reference angles. You can think of this X here, connecting these various angles. An angle has infinitely many brothers in this sense, because remember, coterminal angles are like twins. So the brothers would include all angles coterminal to pi over 6, 5 pi over 6, 7 pi over 6, and these guys. So every angle has infinitely many brothers, as long as it's not quadrantal, like 0 or pi over 2. And why do we care about these brothers? Because it turns out that they're going to have the same cosine value, sine value, and so forth, the same basic trig values up to the sines. They may differ in terms of which values are positive and which values are negative. But in absolute value, they're going to have the same sine values, cosine values, tangent values, and so forth. By value, I could mean undefined. That could be the case for the quadrantal angles. Okay. Now, in addition to this pi over 6 family, and here were computations that explained how to get to the other brothers, because there was a shortcut. And in fact, let's review the shortcut before we get to the other families. Again, what's a quick way of hopping from quadrant to quadrant and getting these brothers? The radian measure actually turns out to be more convenient, more so than the degree measure. Again, let's start with pi over 6 radians. And remember that this trick will extend to these other two families we'll talk about later on, for pi over 4 and for pi over 3. So how do we get the brothers in the other quadrants? 5 pi over 6. Remember, 5 is 1 less than 6. That's the famous brother in quadrant 2. 7 pi over 6. 7 is 1 more than 6. That's the famous brother in quadrant 3. 11 is 1 less than twice 6. 11 pi over 6. That's the famous positive brother in quadrant 4, although often we like this coterminal angle, negative pi over 6. Those patterns extend to the families, these groups of brothers for not just pi over 6, but for pi over 4. Here are the famous positive brothers for pi over 4, and for pi over 3. These are the famous positive brothers for pi over 3. Of course, an angle is its own brother in that sense. Now, coterminal twins have the same trig values, including the sines. So, for example, 11 pi over 6 and negative pi over 6 will have the same sine values, cosine values, tangent values, and so forth, including the sines, positive and negative. Again, for brothers, we have the same values in absolute value, but the signs may differ. Okay, so let's use these ideas of brothers or co-reference angles to look at angles outside of quadrant 1. So for example, before, we talked about the 30-degree angle, or pi over 6 radians. Let's say that we now care about the 210-degree angle, or 7 pi over 6 radians. We know everything about this angle over here, the reference angle. We knew this from the unit circle or the table, but now we're going to figure out how the data for this angle will change or extend out to this angle over here in quadrant 3. Now, many people might prefer the unit circle approach, and we'll discuss that. But first, I'll talk about the right triangle approach, because many students get so used to right triangles. And you can use right triangles, but there's a twist. You have to be prepared to put negative numbers to represent signed side lengths if you have a side that's going down below the x-axis or a side that's going to the left from the y-axis. Be prepared to put signed lengths like these over here. Because remember, 7 pi over 6 is a quadrant 3 angle. It's a bit more than pi radians. We rotate into quadrant 3, where both the x and y coordinates are negative. And from the unit circle approach, we know that the x coordinate is the cosine value, the y coordinate is the sine value. They're both going to be negative. In the right triangle approach, what would we do? Well, you might figure out this right triangle from back in quadrant 1 for the 30-degree angle. For this 30-degree angle, on the unit circle, we have a hypotenuse of 1 unit. The shortest side, which faces the small 30-degree angle, is half the hypotenuse. So this side length here is 1/2. And the medium side here is √3 times as long as the shortest side. So this medium side facing the 60-degree angle will be √3/2, which is √3 times the shortest side, 1/2. Actually, and I'll use another color here, some people might actually prefer to use a circle of radius 2 here if you're dealing with a 30-degree or 60-degree angle. Because if the hypotenuse is 2 units, then the shortest side is 1 unit, and the medium side is √3 units. And then it was easier to think about SOHCAHTOA and figuring out sine, cosine, and tangent. But to make things more consistent, let's keep this as a unit circle, and I'll keep this hypotenuse as 1. So let's look at these red values here. 1/2, √3/2, and 1. In purple, we see the same values in absolute value. The hypotenuse is always positive. We always label the hypotenuse with a positive number or length. This could be 1 meter, let's say. But take a look. On the red triangle, we had positive √3/2 on this side, but for the purple triangle, we're going to put negative √3/2 because this side is going to the left of the y-axis. Likewise, we're going to put negative 1/2 on this leg because this side is extending down from the x-axis. So now we can use SOHCAHTOA relative to this reference angle. I know we're talking about 210 degrees here, but we really want to think in terms of this reference angle when we use SOHCAHTOA. So for example, what is the sine of 210 degrees? The sine of 210 degrees. Right off the bat from the unit circle, we know that it's going to be negative 1/2, which is the y-coordinate of the intersection point. But even on this right triangle, sine, SOH, sine is opposite over hypotenuse. Negative 1/2 over 1 is negative 1/2. So our reading from the right triangle is consistent with our reading based on the unit circle and this intersection point. This intersection point has coordinates negative √3/2. I'm taking the unit circle approach now, comma, negative 1/2. Again, this is the cosine, this is the sine. And I'll tend to prefer the unit circle approach in my notes. But again, if you really like dealing with right triangles, then you can work in this fashion. And if you don't like fractions, you can take 2 as your hypotenuse. So we're going to take the unit circle approach for this in the next lesson.